Hello, boys and girls, and welcome to another episode of your favorite algorithm channel. My name is Ryan Powers, and today I'm going to be taking you through LeetCode 42, Trapping Rainwater. So let's introduce the problem. Given n non-negative integers representing an elevation map, where the width of each bar is 1, compute how much water it is able to trap after raining. So we have this beautiful diagram over here, which depicts the wall heights, which is represented by our input array here. So if we look at our input array, 0 corresponds to a wall height of 0. 1 corresponds to a wall height of 1. And then another 0 here corresponds to a wall height of 0. And then because this wall height here is lower than the one to its left and its right, that's not a hint. Because this 0 here is lower than the wall to its left and its right, it is able to trap water, right? So, I mean, visually, that it's an easy way to kind of think about this problem. We can look at it and dissect it from a visual standpoint and understand where the water is going to be and count it. But the tricky part is how can we programmatically figure out a way to find all of the water that is trapped by all of these different walls. So that is the challenge that I am giving to you, that was forwarded, or that I'm forwarding onto you, that was given to me by LeetCode. That's the problem we're going to be tackling today. And as always, I suggest that you try to figure out the problem on your own first. And if you can't figure it out, or you just want to see how I solved it, then check out the video. Otherwise, if you're ready to get started, come with me to the whiteboard. On the screen here, I have a visual representation of our example problem, albeit a slightly worse visual representation, but a visual representation nonetheless. So what I want to talk about is what is the important information that we can gather to solve this problem. So if we just look at an individual square, let's just look at one. So we're going to look at this square right here and figure out how can we figure out at every square that we are at, how much water could it hold. So we'll look at this square here. And just to make sure that we're all on the same page here, this down here is our array, which represents our wall heights. And this here just tells us how high the current wall is. It's pretty approximate, but that's about what it is. Okay, so let's look at this square right here. How can we tell how much water it has? Well, the water that is contained at any given space, or this space more specifically, is the minimum of the left wall and the right wall minus its own wall. So the wall at that index minus index wall. Okay. So if we look at that, what are these values? Well, this is 1 here, right? So that's a 1. This here, this is a 2. Okay, and then this right here is a 0. So using this this equation right here, we can decipher that the wall height here, the minimum is 1, okay, minus 0. Okay, that equals 1. Great. So we've figured out a way to find out how much water there is at any given space. So let's just add these up here. So that first one is 1. We'll put that over there. Okay. All right, so that first one is 1. We'll put that over here. And now let's look at this space right here, just this, this box right here. How do we figure out how much water there is? Well, let's look at the max wall to the right, the max wall to the left, and then subtract its own wall height to figure out how much water it could hold. So what's the max wall to the left? Well, that's 2. What's the max wall to the right? Well, that's 3. So what's its own wall? Well, that is 1, right? So we'll take the minimum of these two, which is 2, and we'll subtract 1. So that's 1. So we know that we can only hold 1 unit of water here. Great. So we figured out another one. We'll add that one over here. Okay, plus 1. Great. Okay, what about this spot right here? Okay, max wall to the left. All right, well, that's 2. Max wall to the right. Okay, that's 3. So what's the minimum of that? Okay, it's 2. Great. So now we need to just subtract its current wall, its own wall at its own index. Well, that's 0. Okay, great. So we figured out that that's 2. Awesome. So we'll add that up. Actually, get rid of that arrow. We'll add that up. All right. And now look at this spot right here. What's the max wall to the right? Well, it's 3 right here. What about the max wall to the left? Well, that's 2. Awesome. So we know that it can hold a minimum wall height of 2, and then its own wall height is 1. Well, that equals 1. Great. Let's add that up to our current water holding capacity. Okay, let's check this last one right here. Well, what's the max wall to the right? Well, that's 2. Max wall to the left, that's 3. Okay, what's the minimum? That's 2. Okay, minus its own wall height, which is 1. Great. Okay, 1. So we figured out that one. So we know what they all are now. So we can add these up. So 1, 2, 3, 4, 5, and 6. 6. Awesome. So we found our answer. So what's the information that we need? At every index, all we need to figure out is what is the left wall height and what is the right wall height. And then we can subtract the wall height of the current index and get our answer. So this is the strategy we're going to use to solve this problem, and we're going to do it in n time. So we can easily just figure out at each position just by iterating all the way to the end, figuring out what the max is, and iterating all the way to the left, figuring out what the max is there. But we can do this programmatically and store some of this information and use dynamic programming to solve this problem. And that's what we're going to do. So let's go over how that's going to look in the next section. On the screen here, I have 3 arrays. So I have an array for storing our left wall height, max wall height values. We have the heights array, which is just the array representing the wall height at every index. And then we have a right array here, which is going to store the values of our max right wall at every index. So how are we going to do this? How are we going to programmatically fill in the values for the max left wall and right wall as we iterate through this heights array? Well, if we look at our heights array, all we need to do is look at the value to the left of every number and just check to see what is the height of the wall directly to my left. And we can fill that in. Well, there's nothing there. There's nothing here to the left. So the first value we're going to fill in is 0, right? So we're going to fill in 0. And we'll move on to our next value here. And we're going to look to the left here, and we're going to say, okay, well, what is the value of the wall directly to my left? Well, it's 0, but we also have stored up until this point the max wall height that we've seen up until this point, right? So that's comparing that's terrible. That's comparing these two numbers right here, right? So right here, it's just 0 and 0. So at every iteration, we're going to take the max of these two numbers. This number right here is the maximum value that I have seen to this point. And then this value right here is what is the height of the wall directly to my left. So as we fill this in, you'll see that we're updating our max left wall height at every iteration, storing that at every index, which will allow us to solve this problem when we go back through subtracting the left, taking the minimum of the left and right wall height as we discussed before, and subtracting it from the current index to get the amount of water that we could trap at that specific index. So let's go through a round of solving this problem, just to get a better idea of how this is going to work. Okay. So we've already decided that we're going to store 0 at this index here, and we're going to move on to our next index. And we're going to look to our left, and we're going to compare these two numbers. This number being the maximum wall height we've seen to this point, and this other number here being the max or the value directly to the left of the current index we're on. Well, 1 is greater than 0, so we're going to take the maximum, which is 1, and store it at this index. Okay, and now we're going to go to 2, and we're going to check the value directly to its left, and we're going to compare it with the maximum value we've seen to this point. Well, 1 is greater than 0, so we're going to keep 1, and move on to our next value, comparing it to the value in our left and the maximum wall we've seen to this point. Well, 2 is greater than that number, so we're going to keep 2, and we're going to move on to our next value, looking to our left and comparing it to the maximum value we've seen to this point. Well, that's 2 and 1. Well, 2 is greater than 1, so we're going to keep 2. And we're going to move on to our next value. Looking to the value to our left, comparing it to the value, the greatest value we've seen to this point. 2 is greater than 0, so we're going to keep 2. And we're going to keep doing this. Looking to our left, comparing it to the greatest value we've seen to this point, which is 2. So we're going to keep 2. Moving on again, comparing to the value to our left with the greatest value we've seen to this point. Well, 3 is greater than 2. So we can update our max wall height at this index to be 3 for the wall to our left. And we'll look at this value, comparing to our left, comparing with the greatest value we've seen at this point. Well, 3 is greater than 2, so we're going to keep 3. And we'll look at this index, comparing to the value to the left and the greatest value we've seen to this point, which is 3, and 3 is greater, so we're going to keep 3. And then here, we'll look to our left again, and we'll compare with this value and keep 3. Great. So what have we done here? Well, first of all, it looks like I've kind of run off the board here with this array. I didn't line that up very well, but so we'll just put that there. Okay, so what do we have here? Well, in this left array, now we have stored at every single index a reference to the greatest wall height to the left of that current number. So now all we need to do is go through our right wall index, or go through our heights index again, iterating this way, looking at the value to the right, and updating our max right wall. So let's do that really quick. So we'll start here, and we'll look to our right, and we'll see there's nothing there. So we'll fill in a 0. We'll go to here to 2, looking to our left. Well, that's a 1. That's greater, so we'll keep the 1. Now we'll look at this index. Well, 2 is greater than 1, so we're going to keep 2. And now at this index, well, 2 is greater than 1 again, so we'll keep 2. Comparing again, 3, and then what's to the right of our 3 here? Well, that's a 2, and our current max wall height is 2, so we'll just keep 2. And we're going to do this comparing these numbers at every iteration. So let's go ahead and just fill these in. So we have 1 and 3. We'll keep 3. We have 0 and 3. We're going to keep 3 again. Now we have 1 and 3. So we'll keep 3. 2 and 3. Keeping 3. 0 and 3. Still keeping 3. And we'll just fill in 3 all the way to the end. So now that we have gone through and filled out all of the values for the left, which is right here, and our right wall values, which is here, well, we can compare these 3 values together, and we can get how much water we can store at this index. Well, we've already said that we want to get the max or the minimum value of the left and right wall, and then we want to subtract that from the, we want to subtract the index from that value. So what do we get here? Well, our minimum height is 0, so this is gonna evaluate to 0. So we don't have anything here. Our minimum height here is also 0, so so we're not going to get anything from this index either. Well, what about this spot here? Well, our minimum height is 1, right? Because 1 and 3, the min of 1 and 3 is 1, and then we have a height of 0. So we'll do 1 minus 0, and we'll keep 1. Okay, so moving on to our next index, our min height is 1, but our height at this index is 2. Well, that's going to give us a negative number, so we can't store negative water, so we'll just move on to the next one. So what's the minimum height of 3 and 2? Well, that's 2. So we can subtract 1 from that, and that's going to give us a value of 1. So we'll store 1 at that index. So what's the minimum height of 3 and 2? Well, that's 2, and we could subtract 0 from that. Well, that's going to give us a value of 2. And what about here? 3 and 2, well, that's 2 again. Subtracting 1, that's going to give us a value of 1. And then here, we have 2 and 2, but our height is 3, so that's going to give us a negative value. We can't store anything there. Similarly here, that's going to give us a 0 value, so we can't store anything there. What about here? 2 and 3. Well, the minimum value is 2, and the height of this index is 1. So if we subtract 1 from 2, that gives us 1. So we can fill that in here. And then what about here? We can't store anything here, and we also can't store anything here. So what does this all add up to? Well, this is 1, 2, 3, 4, 5, and 6, which is our answer. Okay, great. So now that we've kind of gone through a round of solving this problem, and we have a better understanding of the strategy, let's go ahead and see what this looks like in code. On the screen here, we have our trap function. So we're going to build out all the functionality for this function in our trap function. So the first thing we need to do is create an array to store all of our left wall maxes, right? Our array of left wall references. So let's create a const of left to store all those left walls, and we'll just initialize it as an array with a value 0. So 0 is just going to account for that first index, where when we look to the left, there's no index there. It's undefined, like it's off the array, right? So we're going to initialize it to 0. And then we also need to create a variable, which we'll call right, for storing our right while max. So our right while max, we're just going to update it in real time and calculate our values as we go, because we don't need to store the right while max. We already have the left while max. So as we're going back through the array, calculating the right while max, we can get the amount of water at that index. So we only need to loop through this 2 times. So we'll store that in a variable right. And then we also need a variable total for tracking our totals, right? As we're calculating our sums along the way, we need to total them up. So we'll store that in a variable total. And then we need to loop through our array. So we'll let I be equal to 1, because we don't want to start at that first index. We want to look to the value to the left to get these left wall values. So we'll start at the first index. So we'll let I be equal to 1. And then while I is less than height dot length, well, we want to keep looping. So what are we going to do at every iteration? Well, we're going to push to left the maximum of the left at I minus 1. So the value to the left, or the highest wall value that we've just seen is left at I minus 1. So that's the last value we pushed to our left wall values. And then we want to evaluate the current height that we're looking at in the array. So that's going to be at height I minus 1. So we want the maximum of these 2 values, and we want to store that in our left wall array. So that's all the logic we need for storing these this left wall value. So now what do we need to do? Well, we need to loop back over our array from the other side and get our right wall values. So we'll let we'll define a variable j. So we'll let j be equal to height dot length. And we want to start at -2 because we want to start at the very last index. That's why we're initializing right to 0. We want to start at the very last index, -1, right? Which is going to be height dot length -2. So while j is greater than or equal to 0, we want to keep looping. So we'll do j minus minus. And now we need to recalculate right. So what's right going to be equal to? Well, right is going to be equal to the math.max of right, and then the current wall to the right, which is height at j plus 1. So that's going to give us the maximum wall height at every iteration. And now we can calculate a sum, right? So we can let sum be equal to the minimum, right? We need the minimum of these 2 walls. So it's the math.min of right, our right wall, and our left wall. So that's just going to be our left wall at j. And then we need to subtract the current height of the wall that we're on. So that is going to be height at j. So that's going to give us our sum. So now we just need to check to see if our sum is greater than 0. If our sum is greater than 0, well, then we want to add it to our total. If it's not greater than 0, then we just want to let it pass because we can't collect negative or 0 rainwater. So we're only going to be totaling up our sums of numbers greater than 0. And at the very end, we just want to return our total. So just to do a little bit of recap. So we defined a variable left and we initialized it to 0. So 0 is accounting for that, that index to the left that is not inside of our array. And then we initialize a variable right to 0 to account for our right wall. And we're going to be tracking that as we go. And then we have a total initialized to 0. So we're looping over the array, pushing in at every iteration the maximum of the last wall height that we've seen, the last wall height we've seen, which is our maximum. And then the height at I minus 1, which is the value directly to the left of the current index that we're iterating on. And then we collect the right wall max. So at every iteration, we're reassigning the right wall to be the maximum of the current max right wall, which is right, and then the wall directly to the right of the current index, which is height at j plus 1, because we're iterating from the back. And then at every iteration, we are going to calculate the sum, which is just going to be the minimum of the right wall and the left wall minus the height at that current index. So after we calculate the sum, if it's greater than 0, then we're going to add that to our total. So let's see how we did. Okay, great. 88 milliseconds. Let me run that one more time just to see if we can get a little bit better. Okay. All right, 80. I like that. That looks a little bit better. That makes me feel good. So as always, LeetCode has a conspiracy against me, a conspiracy against all of us because we're learning way too much about algorithms. They're worried that we're not going to need them anymore. So they make our runtimes look terrible. So what are we going to do? We're going to rip the best code to ever grace the presence of LeetCode, and we're going to run it against our code and see who comes out on top. All right, so here we go. Let's see. This looks pretty good here. So let's grab this and go back to our code. All right, great. And we'll paste this in here and run it. Ah, all right. They beat us this time, which is fine. 4 milliseconds. It's okay. I can handle it. Maybe we'll just run it one more time to make sure they're super good. Okay, great. 84 milliseconds. We're in the same ballpark here. Anyway, so I think what I want to point out here is, let's get back to our code because it's cleaner. But what I want to talk about, well, we didn't really talk about the runtime complexity. So what's the runtime complexity of this problem? Well, we're looping once to get the left max wall, right? And then we're looping again to get the right max wall. So we're doing 2 loops through, which is a time complexity of 2n, right? And n is in terms of the array that we're passing in, the height array that we're passing in. But what about the space complexity? Well, the space complexity is also n, right? Because we're storing all those references to our left wall, right? We had to store all of our left wall references so we could calculate the amount of water that we have at each iteration. So our space complexity is also in the order of n. Anyways, I hope you enjoyed this video. I hope you learned something, and I hope to see you in the next one.